Hi everyone. Now today I'm going to explain about excitation tables of all flip-flops in the fifth module. In the preceding lecture, I discussed about different types of flip-flops, all the flip-flops, SR flip-flop, JK flip-flop, D flip-flop, T flip-flop. To understanding of all the flip-flops, you might have known the truth table and logic diagram. For given inputs and present state, then you can define after applying the inputs and considering the present state, you will get the output next state. When we talk about next state in the sequential circuit, that means any memory element or flip-flop, the output which is presently exists is called present state. Nothing but flip-flop is in present state. After applying the clock pulse and giving to the inputs, then what will be the next changing output in the flip-flop is nothing but next state. So with the help of truth table, we can understood we understood that the behavior of the flip-flops, whatever the flip-flop is. Now we will move some extent to that flip-flops, not only understood by the truth table, then we can have different types of tables which will help us to understanding the flip-flops and conversion between them. So what are those tables like? Basically there are truth table and characteristic table and excitation table. The truth table, which gives the behavior of the flip-flop, and the characteristic table is the relationship between the present state and the next state for all the given possibilities of input, by which we can get the characteristic equation for the next state. So with the help of characteristic table, we can get the characteristic equation for each flip-flop. In the previous lecture, already I explained how to get the characteristic equation for characteristic table of each and every flip-flop. Let us see now what is the characteristic table and especially what is excitation table. So our main focus is that excitation table. In the next lecture, we will use this excitation table for conversion from one flip-flop to another flip-flop. So that's why in this lecture we mainly focus on how to make the excitation table for all the flip-flops. If you see that the logic diagram for flip-flop, as we know that, for example, we can make with the SR latch, NAND latch or NOR latch. Let us consider we can have this NAND latch, and by connecting the NAND gated circuit to achieve the SR flip-flop, NAND based SR flip-flop. So we know that if you see the truth table, this is called truth table. This truth table which explain the true values of output by giving different kinds of input combinations. So in this truth table, we know that when clock is 0, whenever 0, no clock is applied. Then the irrespective of S value and reset value, S and R inputs of the SR flip-flop, the output will be remain in the same state. It won't change. There will be no transition between present state to the next state. So ideally, it was in the same state. So irrespective of the S and R when the clock is 0, no change. When we apply any clock, basically we can apply for edge trigger or level trigger, basically edge trigger. When we apply some clock, then for example it is edge trigger from 0 to 1, nothing but 1 high logic 1, represented 1. Then we can observe that for different combinations of S and R, what will be the next state of the SR flip-flop. When clock is high and S is 0 and R 0, that output will be present state only. The next state will be same as in present state. It remains in present state. This is what we can call it as memory. So as long as that the previous present state, after applying the inputs, again next state will be also same thing. That means indirectly we can store the logic values, whether it is 0 or 1 logic values. That's why it is called memory. So, and also indirectly we can get this memory by the present state is feedback to that input of the circuit. We can by getting that delay, it will be maintained, it will be remain in the same state. So that's why it will be act as memory. And also sometimes while designing synchronous or asynchronous circuits, this remain state is called stable state. The flip-flop is in stable state. We can say that that particular state is a stable state. Now let us move to the next case where clock is high and S is equal to 0, R is equal to 1. The output will be 0, which is also called reset. Why it is called reset? So when after applying the when clock is high, set is equal to 0. But now I can turn that reset into 0. When I turn it to reset into 0, 1, then which means which reflects on the output, then in the next state, which gives the 0 output, logic 0, which is nothing but reset of output. Similarly, when we apply for a clock and then set is turned to 0 and reset turned to set is turned to 1, reset turned to 0, then it reflects on resulting in logic 1 in the next state. Logic 1 in the next state. This is called set in the output. And when we apply 1 1 in the SR inputs, you will get invalid, because when both inputs are 1 1 and already clock is high, immediately that is 0 1 1 clock is high, you will get immediately 0. That 0 is applied to latch and latch. Immediately, respect of other inputs, it will get to 1 1. It is invalid for both outputs of flip-flops. So flip-flop outputs always complement to each other. So simply that this truth table will help to the behavior of the flip-flop. Now with the help of this truth table, we can generate the characteristic table. The characteristics table gives gives the relation between input and output, but in that case, at what input and present state combination will get what is corresponding next state. So the main difference is in the truth table and the characteristic table is we will get the next state and present state for all the combinations of S and R. In this, if you see this, if S is equal to 0 and R is equal to 0, of course, we assume that clock is high always. In all the case, the clock is high. By assuming clock is high, Then we can see that what are the combinations of inputs, what will be the present and next state relation. So when S is equal to 0, R is equal to 0, if present state is 0, earlier we don't know, like no, we didn't consider like what will be the, like no, what was the first present state, and after applying the next state what will be the. So directly we can get the general cases in the truth table, but here we can analyze each case. If it is 0 present state, what will be the next state? If it is 1, what will be the next state? So S is equal to 0, R is equal to 0. If present state is Qn is equal to 0, according to this table, so when 0 case, what will be the 0 case? Memory, previous state, present, like next state is equal to present state. So whatever the present state, same state will be reflected in the next state. It won't change. It is in stable state. So now when we can see 0 and then present state is 1. When present state is 1, according to truth table, when 0 the next table will also 1. When S is equal to 0, R is equal to 1, what condition it is in the truth table? S0 R1 reset. Irrespective of present state, the output will be reset. Suppose if 0, present state is 0, whatever the input, the output must be reset, which means 0. The same case, if we assume that the present state is 1, but ultimately it will go to reset. So this is condition for reset and change, like Qn only. Similarly, when we apply 1 0, and if it is present state is 0, the next state must be set. For 1 0 case, the flip-flop, SR flip-flop, the output next state will be set value, irrespective of present state. If it is present state 0, next state 1. If it is present state already 1, again it will be in the same set, will get set. And then if you 1 1 given, according to truth table, whenever 1 1 is applied to SR flip-flop, it is invalid. Whatever the present state, if it is present state 0, invalid. If it is 1, invalid. So we can take that, these 2 rows we can't consider, we can consider as invalid. So this is characteristic table. This characteristic table we can achieve from the truth table. Characteristic table achieved from truth table. When we observe in the characteristic table, all the combinations of S and R and present state to get next state. It is simply by which we can easily get this characteristic equation from the K-map. So I'll explain for one, then we can imagine for all the remaining flip-flops. I'll explain with this one how to get characteristic equation for characteristic table. So in order to get this characteristic equation for next state of SR flip-flop, I am considering this table for Q next is n plus 1. I want to get the characteristic equation for next state. I am taking the 3 inputs. So in order to get the next state, you must have present state and also inputs S and R input. So I am considering here S, R, Q. You can take any K-map. You can take vertically, take S and RQ. You can take Q, S, R. You can take any K-map. I am taking S and RQ. 00011110. So S 0 RQN 0 means. So what are the combinations of logic ones in the next state? 1 1 1 means 0 0 0 1 0 0 1 1 1 double 0 1 double 0 1 101 1 101 1 remaining are last two cases 111 110 11 don't care. So we can get this one quad. This is one prime implicant. So this is 1, this is 2. When we add these two, you will get first one is, what is the Boolean expression for this one? All rows are connected, so cancel to each other. We can consider only S plus what will be the Boolean function, minimized Boolean function for this one, pair. So we can take the row wise cancel to each other, S bar S. Consider the 0 and 1 means R bar Q, R bar Qn. So the next state Qn plus 1 defined in terms of present state Qn and present inputs, like the inputs S and R. So in this way we can achieve this next state from the characteristic table. That is the purpose of characteristics table. Remember it. Characteristic table achieved from truth table, excitation achieved from characteristic table. Now let us see how to get the excitation table from the characteristic table. So what is excitation table? This is the excitation table. Excitation table. This excitation table same here also. We have a present state and next state, and what minimum number of input combinations are required to get the present state and next state. In this excitation table, we have a present state, next state, and other side we have S and R inputs. So that is the relation between present state, next state with respect to inputs. So when present state 0 and the next state will be 0, what will be the required combinations of inputs? So in this case, for the excitation table, we know the present state, we know the next state, and what combinations of S and R that will achieve this one. So let us see now. If Qn is 0, present state 0, and next state is also 0, for what conditions of S and R you will get the present state 0 and next state 0. This can be achieved from the excitation table. If you see this excitation table, what is the combination for present state 0 and next state 0 in the table? So here, this is one case. This is one case, present state 0, next state 0. This is another case, present state 0, next state 0. At what combinations of input S and R for this 0, 0, we will get 0, 0. If you see here, this is 0, 0, R is 0 and 1. So in order to achieve from present state 0, next state 0, present state 0, next state 0, S should be maintained 0 and R will shifted to 0 to 1. So these two combinations can be represented by, if S is 0, R 0, S is 0, R 1, you will get the same output. Q present state 0, next state 0. So this one can be represented by constant representation of S and take the don't care for R, which means S is 0, R don't care means whatever the R. So it will change from 0 to 1. So this can be represented by don't care. So S is constant for two cases. So that's why I am taking S is equal to 0. And R is equal to don't care means it may be whether it is 0, S is 0, R 0, you will get present state 0, next state 0. S is 0, R is also, R may be 1. So then also you can get the same present state 0, next state 0. In this way, we can define the excitation table. If you take the second case, suppose present state 0 and if next state is 1, what happens? If next state is 1, at what input combinations of S and R to get the present state 0 to next state 1? So if you see this one characteristic table, present state 1, next state like present state 0, next state 1, or which case is 0, 1. This is the only case. Present state 0, next state 1. So this is the case. So what is its corresponding combination is 1, 0. So we can take the 1 and 0. And similarly 1, 0. Present state is 1, next state 0. And what combinations of S and R is present state 1, next state 0. This is the case. Present state 1, next state 0. There will be no other case from present state 1, next state 0. So this corresponding input combination is 0, 1. So we can take 0, 1. At last, if present state 1, next state also 1, at what combinations of this one? So this characteristic table, both 1, present state 1, next state 1, present state 1, next state 1. Two cases are there. In these two cases, S value is 0. Sorry, S value is changed from 0 to 1 and R value is kept constant. So that's why I am kept constant of R value. And the changing of S value is represented by don't care. So what is the excitation table now is when present state 0, 0, present state 0, next state 0, 0x, 0, 1, 1, 0, present state 1, next state 0. Its combination is input of 0 and 1. And the present state 1, next state 1, cross x, cross 0. This is the table. Now, this table will help to design like conversion from one flip-flop to other flip-flop. That is the main purpose. So, this is the excitation table for the SR flip. This is the excitation table for SR flip-flop. Now, the same concept will be repeated to the JK flip-flop and D flip-flop and T flip-flop. Now I am directly explained to truth table, then summary of truth table and then characteristic table, from which we can define the excitation table for JK flip-flop. This is the JK flip-flop. As we know that it is made with SR flip-flop by connecting Q, present state Q output is feedback to the K NAND gate and Q bar output is given back to feedback to J NAND gate input. And then we know that the truth table, the simple representation of truth table for JK flip-flop is when clock is 0, irrespective of J and K, it is in the same state, ideally, like an idle mode, or in the same state, it won't change any states. And when clock is high, we can have 4 combinations. If it is 0, 0, it is present next state is equal to present state, which is also called memory. And 0, 1, and it will be treated as reset. And 1, 0, it will be called as set state. And 1, 1, in this case 1, 1, the special case in the JK, like JK, when compared with the SR flip-flop, when 1, 1 input, you will get the complement of next state is equal to complement of present state, QN bar. can call it as a Qn bar. Based on this concept, this table will prepare the characteristic table. This is the characteristic table. This is the truth table. This is characteristic table. What is the characteristic table? All the combinations of J inputs and outputs. So, what happens when J0, K0? When J is equal to 0, K is equal to 0 according to the truth table. When J0, K0, next state is equal to present state. If present state is 0, next state will be 0. When present state is 1 for the same case, next state will be also same because Qn plus 1 is equal to Qn. This is over. Next, if it is 0, 1, we know that whenever 0, 1, the 1 is under K. K means reset indirectly from the because which is made from SR flip flop. K is nothing but R. R we can have a 1 under R, which means reset of output. Whatever the present state, output must be reset. That is called this one. So if it is 0, it will reset to 0. If it is 1, again also it will be reset to 0. Next case, 10 case. If it is 10 case, you will get a set output irrespective of present state. If it is present state 0, output 1. If it is present state 1, again it will be remain in the set state. In the last case, when 1 input in the JK, you will get the toggle output. The next state Qn plus 1 is equal to Qn bar. So this is Qn. It is a complement of Qn is nothing but Qn bar. 0 complement 1, 1 complement is 0. This is next step. Likewise, we can we can get this characteristic table for JK flip flop. With the help of characteristic table, we will get the characteristic equation for Qn plus 1. Qn plus 1 by taking the three variable combination of K map. So the required input variables are J, K, present state to get the characteristic equation for Qn plus 1. So 3 variable K map and then you will get the equation. Maybe that equation Qn plus 1 is equal to J Q bar plus K bar Q. You will get this one Q or Qn, can call it as a Qn. So the next state equation in terms of present state and present inputs. J and Q are present and Qn is the present state. So this is the sequential circle because the present output depends on present input and the present state. Next we will see that excitation table. Excitation table for JK flip flop. We can similarly here also, as we can see in the SR flip flop, same principle we can apply for JK flip flop. Excitation table have present state, next state, on the other side inputs. If it is single input. If it is more than one input, you can take the right side inputs. That is now the relationship between present state, next state, and then input combination. So, and also excitation table. To prepare the excitation table, you must have known the present state and what is the next state. Then what are all the combinations of inputs? You will get that present state, this one, and then next state, corresponding next state. To prepare the excitation table, we know that we can have present state and next state values. For example, Qn is Qn and Qn plus 1. Qn 0 and Qn plus 1 0 at what combinations of S and R will get this 0 0. If you see this Qn 0, Qn plus 1 0, Qn 0, Qn plus 1 0, these two cases, what will be the combination of J and K? So J 0, 0, K 0, K 1. J values remain same, K values transfer from 0 to 1. So that will be represented by J kept constant means can kept the 0, but K is transferred from 0 to 1, we can take the don't care, 0 and don't care. Similarly, we can take the 0 for one case. If present state 0, next state 1, what is the combination in the characteristic table? 0, present state 0, next state 1. Which combination it is? Present state 0, next state 0, next state 1. And present state 0, next state 1. At what combinations of J? J is 1. K is 0 to 1 transfer. K is 0 to 1 change. So take the constant value as it is 1, and changing value can be represented by don't care. Similarly, 1 0 case, if we see this 1 0 case, here it is 1 0, present state 1, next state 0, here it is 1 0. So J value shifted from 0 to 1, K value kept constant. So take the K value constant, and the shifting value is represented by don't care. And if we take 1 1, present state 1, next state 1, 1 1 1 1, what will be the J shifted to 0 to 1? K 0 to 0. So take the constant K and don't care in the J, under J. Likewise, we can prepare the excitation table. 0x, 1x, x1, x0. So this is the excitation table for JK flip-flop. Next, we will see that D flip-flop. We know that D flip-flop made with SR flip-flop by getting the only two combinations to avoid this 0 0 and 1 1 case, especially when both inputs are common, same inputs, we will get some problems in the SR flip-flop. To avoid this one, we can connect it together with the inverter to get the D flip-flop. So delay flip-flop or delay transfer flip-flop. This is the truth table for this D flip-flop. We know the truth table. The truth table, when clock is 0, irrespective of D input, don't care means irrespective of D input, the output won't change. The output T, Qt plus 1 is equal to, or Qn plus 1 is equal to Qt. If clock is high, whatever the D input, same is reflected, same input is reflected to the output of the flip-flop, or the next state is equal to the same input, like present state. The next state is equal to the D value. So whenever I am giving 0 here, that means 0 and inverter output is 1. That 0 1 combination giving to the SR flip-flop, you will get that output is 0. So that means we can simply pass in that D value to the next state. Next state is equal to D. 0 is 0 passing to the next step. If clock is high, when D input is 1, after some time you will get the next step is equal to 1. So next state is equal to 1. So when we observe this one, the next state directly we can write down next state T plus 1 is equal to simply D. That means simply just passing up the D values to the output. So this is observed from the characteristic table. This characteristic table, we can take the all possibilities of D input and present state. If D is 0, present state 0, next state must be 0, just passing. If it is 0, present state 1, but now I am giving D input, that just passing to the D value is next state. So in this case also, we assume that clock is equal to high. When D is equal to 1, present state 0, you can get the output 1. D is equal to 1, present state 1, output 1. So these two columns are same. So that's why the characteristic equation Q n plus 1 or Qt plus 1 is equal to D. And what will be the excitation table? Excitation table for D flip-flop. Excitation table for D flip-flop is relationship of present state, next state with respect to inputs. What you might know, this. In order to prepare this excitation table, you might have known that present state and next state. If present state is 0, next state 0, what will be the D? Next state 0 means simply Qt plus 1 is equal to D means, so we can take this D directly. Otherwise, you can prepared from this excitation characteristic table. At what combinations of D? Present state 0, next state 0. So that combination is D is equal to 0. And present state 0, next state 1. Present state 0, next state 1. Present state 0, next state 1. At what value of D? D value must be 1. Present state 1, next state 0. Present state 1, next state 0. The D must be 0. Present state 1, next state 1. At what combination of D? D is equal to 1. So in this case also, these two are both are same because Qn plus 1 is equal to D. So the excitation table for D flip-flop is, we know the present state, next state we will get the D. That means the same column, second column is copied to output, we will get the D flip-flop. Finally, we will see that T flip-flop. This is the T flip-flop. T flip-flop simply joining of J and K in the JK flip-flop to get the two combinations of JK values. Okay, by giving T is equal to 0, which indirectly means that J is equal to 0, like K is equal to 0. When T is equal to 1, J is equal to 1, K is equal to 1 means toggling case. So in this case, if you see this truth table, when clock is 0, irrespective of 14 input, you will get the same Qt plus 1, no change in the state. When clock is high, when T is equal to 0, indirectly J0, K0. When J0, K0 in the JK flip-flop, like a memory. In the in this case, when J0, K0 will get the same output, present state, Qt. When clock is high, T is equal to 1, nothing but J1, K1. J1, K1 means we know that in the JK flip-flop or truth table, Q1, J1, K1 means complement of output, present state. The next state is equal to complement of present state. So simply just complement of the, complement of present state. Based on this, we can see this characteristic table. What is characteristic table? For all the combinations of input and present state, you will get the next state. If T 0, present state 0, so what will be the present state 0? Next state is also same. Next state is equal to present state because Qt plus 1 is equal to Q. When T 0, present state is 1. Irrespective of present state, T is equal to 0, just copy. Which means when Qn plus 1 is equal to, simply copy. Qn plus 1 is equal to Qn when T is equal to 0. Because when T is equal to 0 means unchanged in the JK flip-flop. So T is 0 means J0, K0. Next, T is equal to 1 case. When present state 0, complement 1. When present state 1, complement of out. So in this way we can get the characteristic table by which we can make the excitation table. Excitation table, we know that present state, next state, what will be the combination of t? Present state 0, next state 0, t must be 0. If qn 0, qn plus 1, 1, it would be, t would be 1 because complement. Present state to next state complement each other. It would be 1. One or 0 complement, t would be 1. If present state 1, next state 1, t would have been 0 because no change in the state. Present state to next state, t 0. When t 0 0, no change in the present state next state. When t 1, complement in the state, present state to next state. So this excitation table for T flip-flop will help to convert from T to any other flip-flops. In this way we can get all the excitation table. When we know the excitation table, it will be easy to understand the conversion between flip-flops. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.